Hello everyone. Today our topic is sequence and infinite series. And welcome back to our channel. So let us see what is sequence. What is a sequence? A collection is of real numbers, not necessarily distinct, is said to be a sequence of numbers if corresponding to every positive integer n there exists a unique element of s. Okay. See, the element of s corresponding to positive integer n is denoted by an. Now let us say a sequence consisting of a1 a2 in this way is usually denoted by within parentheses a1 a2 in this way, or simply a sequence is represented as an within parentheses. So if we take example of sequence, then it may be, let us say, 5 7 9 11 is a finite sequence. We can say 1 1 by 2 1 by 3 1 by 4, that is an sequence an where an can be denoted as 1 by n. If you put 1, you will get 1 by 1. If you put 2, you will get 1 by 2. If you put 3, you will get 1 by 3 in this way. So an 1 by n is this an is a sequence, and this sequence is known as harmonic sequence. You take another example. Let us say the sequence an where an is 5 for all n is a constant sequence. That is, our sequence is 5 5 5 in this way. So this is a constant sequence. Now if we take another example, let us say the sequence an where an is half 1 plus minus 1 to the power n minus 1, where n is a natural number. So what would be the sequence? The sequence is, we put 1 here, you will get 0, you will get 1. 1 plus 1 2, 2 by 2 is 1. You put 2 here, so 2 minus 1, that is 1, minus 1 to the power 1 is minus 1, 1 minus 1 is 0, 0 by 2 is 0. Again, if you put 3 here, you will get 1 and 0 in this way. This is also a sequence. Now, moving forward, next topic is monotone sequence. Monotone sequence. So in this monotone sequence, we have monotonic increasing sequence and monotonic decreasing sequence. So let us see one by one. First one is monotonic increasing sequence. So let me write the definition first. So the definition is a sequence an of real numbers is said to be monotonic increasing if a1 is less than equals to a2 is less than equals to a3. In this way it will go. That is, we can say ai is less than equals to ai plus 1. So if you put 1 here, so a1 is less than equals to a2. If you put 2 here, a2 is less than equals to a3. In this way, for I equals to 1, 2, 3. Now let us see monotonic decreasing sequence. Okay. So the definition would be same. A sequence an of real numbers is said to be monotonic decreasing if a1 is greater than equals to a2 is greater than equals to a3. In this way it will go. That is, we can say ai is greater than equals to ai plus 1. Remember all these things because in the later section we will apply all these things. Okay, so remember step by step. For I equals to 1, 2, 3. So a sequence is monotonic increasing sequence if ai is less than equals to ai plus 1, and it is a monotonic decreasing sequence if ai is greater than equals to ai plus 1. Okay, now let us see what is monotonic sequence. What is monotonic sequence? Okay, a sequence an of real numbers is said to be monotonic if the sequence an is either monotonic increasing or monotonic decreasing. In that case, we call this sequence an as monotonic sequence. It can be monotonic increasing or it can be monotonic decreasing. Okay, but if you notice this sequence 1 0 1 0 in this way is neither monotonic increasing nor monotonic decreasing. Okay, this sequence is neither monotonic increasing nor monotonic decreasing. Okay, now let us move forward to our next topic, which is bounded sequence. Bounded sequence. See, a sequence an of real numbers is said to be bounded above. So let me write it here. This sequence of real numbers is said to be bounded above, is said to be bounded above if there exists a real number capital M such that an is less than or equals to m for n equals to 1 to 3 in this way. So remember this. This sequence of real numbers is said to be bounded above if there exists a real number m such that an is less than or equals to m. We say it is bounded above. This is bounded above. If an is less than or equals to m, we call it bounded above. And we call bounded below, if there exists a real number, if there exists a real number small m such that an is greater than or equals to small m. So in that case, we call it bounded below. If an is greater than or equals to small m, where m is a real number, then this is bounded below. And if an is less than or equals to capital M, where m is a real number, we call it bounded above. Okay. So we can say that a sequence an of real numbers is said to be bounded if the sequence is bounded above as well as bounded below. So let me write it here. A sequence an of real numbers is said to be bounded if the sequence is bounded above as well as bounded below. Only then we can call that sequence as bounded. So we can say that a sequence n is bounded if there exists a positive number, let us say k, if that an is, if mod of n is less than or equals to k. And we know this means an lies between minus k to k. N is 1 to 3. So in this condition, we can say that the sequence is bounded because for n greater than or equals to m, it is bounded below and an less than equals to, for this case we know it is bounded above, and for this case we know it is bounded below. So the sequence is bounded above as well as bounded below. So that's why this sequence which satisfies this condition, we call that sequence a bounded sequence. Okay. So let us see one example. Let us take a sequence an where an is 1 by n square. That is the sequence. If we put 1, it will be 1. If we put 2, it will be 2 square. If we put 3, it will be 3 square, in this way. This sequence is bounded because we can say that an is between 0 to 1, right? The value is between 0 to 1. If you put 0 only, then you will get 0. Otherwise, all these values are less than 1. So it is satisfying bounded above and bounded below condition. So this sequence is bounded sequence for all positive integer n. Okay. Now, if we take another example, let us say we have a sequence n where n is defined as 3 to the power n minus 1. So what is the sequence? Sequence is, if you take 1, it will be 3 to the power 0, that is 1. If you take 2, 2 minus 1 is 1, so it will be 3. 3 square, in this way. So it is continuously increasing. So we can say that this sequence is not bounded. This sequence is not bounded. Okay. It is bounded below, right? Because an is greater than equals to 1 for all n belongs to a natural number. That is, it is always bounded below. Okay. But it is not bounded above. So it is not bounded. Now, if we take limit of a sequence, what will happen? So let us see. Limit of a sequence. So let me write it here, the definition. A sequence an of real numbers is said to tend to a limit L if for every epsilon greater than 0 there exists a positive integer, there exists a positive integer n depending on epsilon such that for every n greater than capital N, mod of an minus L is less than epsilon. So if these conditions are satisfied, we can say that limit n tends to infinity an, this value gives L. Okay, that is an tends to L if n tends to infinity, right? So this is the limit of a sequence, as simple as that. Now moving forward to our next part, which is convergent, divergent, and oscillating sequence. So let us see one by one. First is convergent sequence. So see, a sequence is convergent if limit n tends to infinity an is finite. That means limiting value of an gives a finite value. Then we call that sequence an as convergent sequence. If we take one example, let us see one example. We talk about this sequence 1 by 3 1 by 3 square up to 1 by 3 to the power n. So that is, the sequence is an, let us say, where an is 1 by 3 to the power n. Now this is convergent. Why? If you put limit here, if you put limit n tends to infinity 1 by 3 to the power n, so 3 to the power infinity is 1 by infinity, that is 0. So it's a finite value. So that means we can say that this sequence or this sequence is a convergent sequence. So simply remember, if that limiting value gives a finite value, then that sequence will be convergent. Now let's talk about divergent sequence. So if this limiting value is not finite, then that sequence would be divergent sequence, right? So you can say limit n tends to infinity an is plus infinity or minus infinity. In that case, that sequence would be divergent. Now if we take one example, let us say we have a sequence an where an is n cube. This is divergent, right? Because if we take limit n tends to infinity n cube, this will be infinite. So this is a divergent sequence. Now let's talk about oscillating sequence. So oscillating sequence means it is neither convergent nor divergent. So let us take one example. If we have sequence something like this, minus 1 1 minus 1 1, in this way, that is, we can say minus 1 to the power n is the n. This is oscillatory, right? Because let us say our n is minus 1 to the power n. If we take limit n tends to infinity a of 2n, a to n, then this will be limit n tends to infinity minus 1 to the power 2n. So minus 1 square is always positive. So it will be plus 1. And if we take limit n tends to infinity a 2n plus 1, this would be limit n tends to infinity minus 1 to the power 2n plus 1. This would be minus 1 because it's an odd number. So we can say that this is oscillatory. It is neither convergent nor divergent. So this limit n tends to infinity an does not exist. Okay, so it is a oscillatory sequence. Now let us see some theorems. So our first theorem is a convergent sequence determines its limit uniquely. A convergent sequence determines its limit uniquely. Okay, so always remember, if a sequence is convergent, then it has a proper limiting value. This is all about this theorem. Theorem 2 is every convergent sequence is bounded. Every convergent sequence is bounded. Okay, so that means it should be bounded above and bounded below. This is all about theorem 2. Now let us see theorem 3. Monotonic increasing sequence which is bounded above is convergent and converges to its exact upper bound or supremum. See, we don't have the proof of these theorems in our syllabus and we don't require this. Just the thing is that you have to understand the theorems and move on. A monotonic increasing sequence which is bounded above is convergent. So that means if there is a monotonic increasing sequence, and we know all this, and that monotonic increasing sequence is bounded above and is convergent, and that convergent value is converges to its exact upper bound or supremum. So bounded above, right? So bounded above means this condition, and it will take this value. This is known as supremum. Okay, Now our theorem 4 is opposite to this theorem. A monotonic decreasing sequence, monotonic decreasing sequence bounded below is convergent and converges to its exact lower bound. Exact lower bound. Okay, it converges to its exact lower bound. That means this value, small m value. Now let us talk about theorem 5. A monotonic increasing sequence diverges to plus infinity if it is not bounded above. Okay, if you have monotonic increasing sequence and which is diverging and gives plus infinity, when it is possible when the sequence is not bounded above. Now opposite to is theorem 6. This is a monotonic decreasing sequence diverges to minus infinity if not bounded below. Okay, is opposite to theorem 5. Now let us see one question. If that the sequence xn where xn is 1 plus 1 by n to the power n is convergent. In the later section, we'll learn some shortcut methods to solve this type of question. Now, let us see how to solve at this moment. Firstly, we have to show that it is convergent. So it will be sufficient enough to show that the given sequence is monotonic increasing and bounded above, right? Now we know the binomial theorem. Our xn is 1 plus 1 by n to the power n. And if we apply binomial theorem, that is, this is our 1 plus x to the power n formula, and we know the formula, that is 1 plus nx plus n into n minus 1 by 2 factorial into x square plus n into n minus 1 n minus 2 by 3 factorial into x cube, that is 1 by n cube. And in this manner, n into n minus 1 n minus 2 and 3 to 1, because it is decreasing, divided by c, this is 1 factorial, this is 2 factorial, this is 3 factorial, so last one would be n factorial, into 1 by x to the power n, that is n to the power n, right? Now this is 1, this n and n will cancel out, this is 1, this is 1 by 2 factorial, and if you write, if you, this 1 n will cancel out, n by n is 1 and 1 by n is 1 by n, so it will be 1 minus 1 by n plus 1 by 3 factorial, this n 1 n will cancel out, you have n square. If you divide by n here and divide by n here, you will get 1 minus 1 by n and 1 minus 2 by n. In a similar manner, you will get 1 by n factorial, 1 minus 1 by n, 1 minus 2 by n, in this way 1 minus n minus 1 by n. So now if we replace n by n plus 1, replace n by n plus 1, we will have, this is our xn, right? This is our xn. So we will have x of n plus 1 as 1 plus 1 plus 1 by 2 factorial, 1 minus 1 by n plus 1 plus 1 by 3 factorial, 1 minus 1 by n plus 1 into 1 minus 2 by n plus 1, says 1 by n plus 1 factorial, 1 minus 1 by n plus 1, 1 minus 2 by n plus 1, up to 1 minus n by n plus 1. Sorry. Okay. This. Now let us say this is our 1 number equation and this is our 2. So from 1 and 2, you can observe that the first two terms are equal. The first two terms are equal. And we also observe that 1 by n plus 1 is less than 1 by n, right? Because we know 1 by 3 is less than 1 by 2. So we can say that 1 by n plus 1 is less than 1 by n. If we multiply by minus on both the sides, we will get minus 1 by n plus 1 this less than will be greater than minus 1 by n. If you add 1 on both the sides, it will be 1 minus 1 by n plus 1 is greater than 1 minus 1 by n, and so on, except for the first two terms, right? So every term of, except for the first two terms, every term of xn plus 1 is greater than corresponding terms of xn, right? So remember this, we found out that every term of xn plus 1 is greater than term of corresponding term of xn, okay. Now you can also observe that xn has n plus 1 terms, while xn plus 1 have xn plus 2 terms, okay. So you can write it down. Xn has n plus 1 terms and xn plus 1 have n plus 2 terms, okay, because this series starts from 0 and total n terms. So in xn there are n plus 1 terms, and we have increased by 1 here, n plus 1, so you will have n plus 2 terms. So we can say that xn plus 1 is greater than or equals to xn for all n belongs to natural number, that is the sequence xn is monotonic increasing, okay. Now if you notice that xn is greater than or equals to 2 for all n belongs to n natural number, because see, we will get at least 2, whatever value comes here we will get at least 2 and higher. So xn is always greater than or equals to 2 for all n belongs to natural number. That is, you can conclude that the sequence xn is bounded below. Sequence xn is bounded below. And what is the lower bound? The lower bound is 2. And 2 is a lower bound. 2 is a lower bound. Also, we can see that xn is 1 plus 1 plus, let me write it here, 1 by 2 factorial, 1 minus 1 by n plus 1 by 3 factorial, 1 minus 1 by n, 1 minus 2 by n. In this way, 1 by n factorial, 1 minus 1 by n, 1 minus 2 by n, 1 minus n minus 1 by n. This is less than, we can say 1 plus 1 plus 1 by 2 factorial plus 1 by 3 factorial up to 1 by n factorial. This whole thing is less than this, right? You can say, because 1 subtracted with something, it will be a less value. So this thing is always less than, if we omit 1 minus 1 by n, 1 minus 1 by n, 1 minus 2 by n, all these terms. So this whole thing is less than this thing, right? So you can say this is less than 1 plus 1 plus 1 by 2 plus 1 by 2 to the power n up to 1 by 2 to the power n minus 1. This term is again less than this term, because if you see 1 is same, 1 is same, 1 by 2 factorial is 2, no issues. 1 by 3 factorial is 3 into 2, that is 6. And if you put 2 here, then you will get 4, right? So this term is less than this value, we can say. So let us say this is 1 plus, and this thing is a GP series with common ratio half. So A into A is 1, 1 minus r to the power n by 1 minus r, that is the formula. 1 minus r to the power n by 1 minus r. So this is 1 plus 1 minus half to the power n by half. So this will be 1 plus 2 minus 2 to the power n minus 1, because it would be 2 to the power minus n and it would be 2 to the power minus 1. So if you multiply by 2, this will be 2 to the power minus n plus 1. Okay. If you simplify this, you will get 2 multiplied by 2 to the power minus n plus 1. So this thing would be, let me check here, this would be multiplied by 2. This is 1 minus 2 to the power minus n. So it would be 2 minus 2 to the power minus n plus 1. It would be minus n plus 1. Okay. So you can say this is 3 minus 2 to the power minus n plus 1, and which is always less than 3. So I can say that xn is less than 3 for all n belongs to natural number. So it is confirmed that the sequence xn is bounded above. So we have proved that it is bounded below by this, and by this we have proved that this is bounded above. So we can say that the sequence is bounded, because it is both bounded above and bounded below. So we can say that the sequence xn is monotonic increasing and bounded. So it is convergent. So we can conclude that Xn is monotonic, increasing, and bounded, so it is convergent. So it is convergent. Okay. So we have proved. Now let us see our next topic. See this, we have methods to solve or to show convergence. We will check and we will learn different theorems regarding convergency. So don't worry about this, because it's a long method, and if you don't have practice this type of question, you will not be able to answer in the exam. So we'll learn theorems to solve this type of question. So moving forward, we have theorems on limits of sequence. Okay, let us say xn and yn be two sequence such that limit n tends to infinity, limit n tends to infinity, xn is a, and limit n tends to infinity, yn is b. So we have theorems, that is, we can say then number one is limit n tends to infinity, xn plus yn, you can write it as a plus b, because limit n tends to infinity xn is a and limit n tends to infinity yn is b, so it is a plus b. Next we can write limit n tends to infinity, xn minus yn is a minus b, limit n tends to infinity, xn into yn would be a into b, and number 4 is limit n tends to infinity, xn by yn would be a by b, provided b can never be 0. Okay, so these are simple applications. Now let us see some questions regarding convergency, then we will move forward to our next topic. Let us say our first question is, if xn is 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4 up to 1 by n into n plus 1, then show that xn is bounded monotonic increasing sequence. So let us see the solution. So xn is 1 by 1 into 2. We can write it as 1 minus 1 by 2. And 1 by 2 into 3. We can write it as 1 by 2 minus 1 by 3. Because if you take LCM, you will get the same thing. In the similar manner, we will get 1 by 3 minus 1 by 4 and 1 by n minus 1 by n plus 1. So see, these values are cancelling out. So this will cancel out. So we will get 1 minus 1 by n plus 1. That is n plus 1 minus 1, that is n by n plus 1. Similarly, we can say x of n plus 1 is putting n plus 1 in place of n. So it will be n plus 1 by n plus 1 plus 1, that is n plus 2. If we take the difference xn plus 1 minus xn, it will be n plus 1 by n plus 2 minus n by n plus 1. It will be 1 by n plus 1 into n plus 2. So this thing will always be greater than 0, right? For all n belongs to natural number. So we can say that xn sequence is a monotonic increasing sequence. Okay, we can say that xn is a monotonic increasing sequence. Now see, xn is greater than 0, right? Because this n by n plus 1 is always greater than 0, right? Since n by n plus 1 is greater than 0. Okay, and we can say also that xn, which is n by n plus 1, is less than 1, right? If you take 1, 1 by 2. If you take 2, 2 by 3. So it will be always less than 1 for n belongs to natural number. So we can say that xn lies between 0 to 1. That means it is bounded. That means it is bounded. So it is monotonic increasing and bounded. Okay, so we can say xn is monotonically increasing and bounded. Okay, so I think you have come to know that how to solve this type of question. All these question follows the same process. You just have to follow the process. Let us see our next question. We have to evaluate this. Limit n tends to infinity. 1 cube by n to the power 4 plus 2 cube by n to the power 4 plus 3 cube by n to the power 4 up to n cube by n to the power 4. Okay. So let's see the solution. If you take n to the power 4 or if you take LCM, this limit will be limit n tends to infinity. This will be n to the power 4, 1 cube plus 2 cube plus 3 cube up to this n cube. And we know the formula of this. This is n into n plus 1 by 2 whole square, right? N into n plus 1 by 2 whole square. This is the formula of this. Sum of cubes of n natural numbers into 1 by n to the power 4. So we get n square into n plus 1 square upon 2 upon 4 n to the power 4. And we have a limit outside. Limit n tends to infinity. Okay. Now this will cancel. You will get square, and if n square, if you divide this, you will get limit n tends to infinity 1 plus 1 by n square. N is infinity, 1 by infinity is 0. So this will be, here you have 1 by 4 outside. So you will have 1 by 4 as the answer. Okay. Now see another question, that is, show that the sequence xn where xn square root of n square root of n plus 1 minus square root of n is convergent. So for convergence, we know that we have to take the limiting value, and we have to prove that it has, the limiting value has a real number. So let's prove this. First of all, rationalize this. So xn is square root of n plus 1 minus square root of n. So first rationalize. This is square root of n plus 1 plus square root of n, multiplying and dividing by square root of n plus 1 plus square root of n. So it will be a minus b, a plus b, that is a square minus b square. So square root of n and a square minus b square. Square root of n plus 1 square is n plus 1, and square root of n square is n, divided by square root of n plus 1 plus square root of n. So it will be n cancels out. It will be square root of n by square root of n plus 1 plus square root of n. If you divide by square root of n in the denominator, it will be 1 by square root of n plus 1 by n, and outside it is 1. Square root of n by square root of n is 1. Now we have to take the limiting value. This limit n tends to infinity x of n, that is limit n tends to infinity of this value square root of 1 plus 1 by n plus 1. If you take infinity, 1 by infinity is 0, 1 by 1 plus 1 is 2. So half. That means we got a real number. Finite value, right? We got a finite value. So we can say that this sequence xn is convergent. Okay, that's how we have to prove this type of problem. Now moving forward to our next topic, which is infinite series. So if you have a sequence which is going up to infinity, u1, u2, un up to infinity, then this is known as infinite series. Okay, and this infinite series is usually denoted by or denoted as summation of n equals to 1 to infinity u of n. And if you don't write 1 or n, you can define infinite series as summation of un only. This is also valid. Okay, summation of un means n 1 to infinity. Now let us see convergent series. Convergent series. A series u of n, summation u of n of a real number is said to be convergent, and convergence to u if the sequence, let us say we have a sequence s of n, is convergent. And we can say that limiting value of Sn is u of n. Limiting value of Sn is u of n or u, where Sn is u1 plus u2 up to these terms. Okay, and here we have written down u as this thing. Summation of un we have written down here as u. This u means summation of un. That means this thing. Summation n 1 to infinity u of n. This is u. Okay. Now let us take one example. Now let us say, let us see by one example. Let us consider one series, that is 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4 up to infinity. Let us take u of n as 1 by, that is nth term, as n into n plus 1. If you put 1, you will get this term. If you put 2 here, you will get this term. 2 into 2 plus 1, that is 2 into 3. And we can write this term as 1 by n minus 1 by n plus 1. Okay. Now see, what will be our un? U of 1, it will be 1 minus half. What will be u of 2? If you put 2 here, it will be half minus 1 by 3. In the similar manner, u of 3 would be 1 by 3 minus 1 by 4. So we can say u of n is 1 by n minus 1 by n plus 1. So what would be the Sn? Sn would be summation of 1 plus u2 plus u3, all these terms are summation of Sn. So here we can see that this term will cancel out. So it remain with 1 minus 1 by, this is the first term, and this last term, 1 minus 1 by n plus 1. Okay. Now if we take the limiting value, limit n tends to infinity, s of n is limit n tends to infinity 1 minus 1 by n plus 1. If n tends to infinity, 1 by infinity is 0, so you will get 1. So we write now let us move forward. See, we write summation of un is infinity or minus infinity according as limit n tends to infinity, s of n is infinity or minus infinity. Let us take one example regarding this, so it will be more clear. Whether you are doing BSc or whether you are doing engineering or any other competitive exam, remember one thing, that the more examples you take, the more understanding you will get. Let us consider one series, that is 1 square plus 2 square plus 3 square to n square. So here nth term is n square. So you can say Sn is u1 plus u2 plus u3, right? So u1 is 1 square, u2 is 2 square, all these terms. So this is sum of square of n natural numbers. So we know the formula, n into n plus 1 into 2n plus 1 by 6. Now if you take limit n tends to infinity, s of n, that is limit n tends to infinity, n into n plus 1 to n plus 1 by 6. This would be infinity, right? If you put infinity, you will get infinity. So you can say that the series is divergent. The series is divergent and diverges to plus infinity. So that's why we tell here that summation of un is plus infinity or minus infinity according to limit n tends to infinity, Sn is infinity or minus infinity. Now oscillatory series. Oscillatory series. A series summation of un of a real number is said to be oscillatory if the sequence Sn is oscillatory, right? If Sn is oscillatory, then summation of un will also be oscillatory, right? Where Sn is u1 plus u2 in this manner, un. So we know already that if a series is neither convergent nor divergent, that series is known as oscillatory, and we have seen one example regarding this. Okay. Now we have two important infinite series. So let us discuss one by one. Number one is geometric series. So the series summation x to the power n this 1 plus x square. If you put 1, if you put 2, if you put 3 here, you get this up to infinity. Is known as geometric series with common ratio 1. X by 1 is x, x square by x is x, so common ratio is x. So let us see the theorem regarding this. A geometric series summation x to the power n is convergent if minus 1 less than x less than 1 and divergent if x is greater than equals to 1 and oscillatory if x is less than equals to minus 1. So remember, this is a very important theorem. We will use this. This geometric series, that means this series, is convergent if x lies between minus 1 to 1. It is divergent if x is greater than 1, greater than equals to 1, and it is oscillatory if x is less than equals to minus 1. Okay. So let us see one example. It will be more clear. We have a series, something like this. 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube to infinity. Now see, this series is convergent, right? This is convergent because its common ratio x. What is x? X is the common ratio of this GP, right? So here x is half by 1 or 1 by 2 square by half, that is half, and half is less than 1. It is between minus 1 to 1. So it is convergent. So this series is convergent. So this is number 1, that is geometric series. Now let's see our next series, which is P series. The P series. Now from onwards, you have to be very serious because whatever you will learn will definitely come into your exam. The series one by 1 to the power p plus 1 by 2 to the power p plus 1 by 3 to the power p up to infinity, that is the series summation n equals to 1 to infinity 1 by n to the power p is called P series. Okay, so we have theorem regarding this to find out the convergent and divergent. The P series is convergent if p is greater than 1 and divergent if p is less than equals to 1. That's all you have to remember. The P series will be convergent if p is greater than 1 and it will be divergent if p is less than or equals to 1. Okay. Now let us see some properties of infinite series. properties of infinite series. Okay. First property is, if summation of un is convergent and summation of un is s, then summation of k into un is convergent and summation of k into un is k into s, because summation of un is s and k is constant, so we can take it outside the summation, so it will be k into summation of un, that is k into s, where k is a constant. Okay, so let us see property number 2. If summation of un is divergent, then summation of k into un is divergent where k is a constant. Property number 3 is, if summation of un and summation of vn are convergent and converges to s1 and s2, then the series summation k1 un plus k2 vn is also convergent, and you can write summation of k1 un plus k2 vn as k1 s1 plus k2 s2, where k1 and k2 are constant. Okay. Number 4 is, the character of convergency or divergency of an infinite series remains unaltered by the addition or removal of a finite number of terms. So if you remove finite number of terms from a series, the convergency or divergency will remain same. Okay, so you can write it down. We have some theorem, so let us see. Theorem 1, that is, if the series summation of un of real numbers is convergent, then limit n tends to infinity un is 0. Okay, so but remember, this converse of this theorem is not true. Converse of above theorem is not true. Remember this. Because let us see one example. Let us consider a harmonic series. Harmonic series summation 1 by n. This summation 1 by n is a harmonic series. It is divergent, right? It is divergent. But if you take limit n tends to infinity, 1 by n, 1 by infinity is 0. So limiting value is 0, but it is divergent. But the theorem is if summation u of n of real numbers is convergent, then limiting value will be 0. But you cannot say the reverse. If limiting value is 0, then it will be convergent. You cannot say that. So our theorem number 2 is this is series of applicable for series of positive terms. Series of positive terms. Positive term series either converges or diverges to plus infinity, not oscillatory. Remember this. If you have a positive term series, it will either converge or diverge to plus infinity, but it will never be oscillatory. Now, moving forward to our next topic, which is power series. Power series. Series of the form, a series of the form summation n equals to 0 to infinity a n x minus x naught to the power n, that is if we put 0 it will be a0 plus if you put 1 it will be a1 x minus x0 here 1, so a2 x minus x0 square, in this way it will go, and an x minus x0 whole to the power n. And if here x0 is 0, we can say summation n equals to 0 to infinity an x to the power n will be a0 plus a1x plus a2x square. In this way, an x to the power n, where the coefficients a0, a1, a2 are independent of x and is called a power series in x. Okay, this is your power series in x. Okay, and from this we can conclude that the simplest and most important, simplest and most important power series is the geometric series. It's also a power series, okay, where all the coefficients are 1. So 1 plus x square, there is a geometric series where all the coefficients are 1. So from all this discussion, it is evident that the above geometric series is convergent and mod of x is less than 1. Okay, when x this is converges or convergent, we can say, if x lies between -1 to 1 and it is diverges if x is greater than equals to 1 and it is oscillatory if x is less than -1. So we can say that as the variable x in a power series changes, the terms also change and the series may undergo a change from a convergent to a non-convergent. So we can conclude that a power series in x may be convergent for all values of x or for a certain range of values of x or for no values of x except 0. So it is therefore important to determine the value or the values of variable x for which a power series is convergent. That is why the idea of interval of convergence of a power series arises. Okay. Now let us see what is interval of convergence. Interval of convergence. See, the definition is the interval of convergence of a power series in x is a set or the collection of values of x in an interval such that the series is convergent for each values of x in this interval but is not convergent for values of x outside the interval. So if a power series, let us say summation a n x to the power n, this is a power series, converges absolutely for all values of x inside the interval just now we have seen, if x lies between -1 to 1, or we can say it converges if x lies between -r to r and it diverges if x is greater than equals to r or greater than r, or mod of x greater than r, where r is called radius of convergence. R is called radius of convergence of the power series. Okay. So if we take example, the power series summation n equals to 1 to infinity x to the power n has interval of convergence as interval of convergence is between -1 to 1. Okay. Now let us move forward. That is test of convergence of series of non-negative terms. This is important section. Please be careful. Test of convergence of series of non-negative terms. Okay. So we have certain theorems and certain proofs to test the convergency. That is, let us see one by one. And we will solve one question from each section so that idea will be clear. First one is comparison test. First one is comparison test. So let us see the theorem regarding this. This should be our theorem 1. Let summation un and summation vn be the two series of positive numbers and summation vn is convergent. Then summation u of n is convergent if number 1 there exists an integer n such that u of n is less than equals to k into v of n for all n greater than equals to natural number where k is a constant. Okay, here remember k is a constant. Okay, and number 2 is limit n tends to infinity u of n by v of n is L, where L is a finite number. Where L is a finite number. It may be 0. Remember, it may be 0. And so it is very useful theorem. If you have two series positive numbers and if you know that Vn is convergent, then Un will be convergent if there exists an integer n such that Un is less than equals to k into Vn, and or this thing. So in maximum number of cases we will apply this limiting value of n tends to infinity Un by Vn should give a finite number. We will apply this thing in maximum number of questions. And let us see theorem 2 regarding this. Let summation un and summation Vn be two series of positive numbers and summation Vn is divergent, then the series summation Un is divergent if number one, there exists a positive integer n such that E1 is greater than equals to k into V of n. Here see, for convergence Un is less than equals to k into Vn, but for divergence Un should be greater than equals to k into Vn. For all n belongs to natural number, n is greater than equals to natural number and k is a constant. Or we can say if limit n tends to infinity, u of n by v of n, u of n by v of n is L, where L is a non-zero number. Okay, L may be infinite. Okay, let us see theorem 3. Don't worry about this, we will see questions and it will be very clear. Let us first see all the theorems. So theorem 3, let summation Un and summation Vn be two series of positive numbers then number one, if u of n by u of n plus 1 is greater than v of n by v of n plus 1 for all values of n, and summation of Vn is convergent, then the series summation of Un, this is Un, is also convergent. Okay, number 2 is if u of n by u of n plus 1 is less than v of n by v of n plus 1 for all values of n, and summation of v of n is divergent, the series summation of u of n is also divergent. So what you have to do, you have to check this first if it is greater than or less than. So according to Vn, if Vn is convergent, then Un will be convergent. If Vn is divergent, Un will be divergent. That's all you have to check. Now, let us see some questions regarding these theorems so that this topic will be crystal clear. So, our first question is, test the convergence of the series 6 by 1 into 3 into 5 plus 8 by 3 into 5 into 7 plus 10 by 5 into 7 into 9, in this way. So let's see the solution of this question. Let us say Un denotes the nth term of the given series. So what will be the nth term of this series? What will be the nth term of this series? See, we can write this series as 2n plus 4 by 2n minus 1 to 2n plus 1 to 2n plus 3. This is the critical thing. In the exam, you just have to find out the nth term. Only then it will be very easy. See, if you put 1 here, so 2 plus 4 is 6. This will be 2 minus 1 is 1. This is 2 plus 1 is 3, and this is 2 plus 3 is 5. So in that case, if you put 2, you will get this term. So our nth term would be this. Okay. Now, see, in this ratio, the denominator power is n into n into n cube. The numerator is n. Okay. So degree of expression in the denominator minus degree of expression in numerator, it would be 3 minus 1, that is 2. So the power in the denominator is n into n cube, and power in the numerator is n to the power 1. So what is the difference? This is n cube, that is 3. This is n to the power 1, that is 1. So 3 minus 1, that is 2, is the difference. So we have to take that Vn. That Vn we can assume as 1 by n square. That's why we have found out this. So let Vn is 1 by n square. Now see, we know, first check limit n tends to infinity u of n by v of n. Okay, so it would be limit n tends to infinity u of n by v of n. So n square will be in the upper side. So n square into 2n plus 4 by 2n minus 1, 2n plus 1 into 2n plus 3. If you divide by n square in the numerator and denominator, you will get limit n tends to infinity 2. If you divide by n here, so it will be, or if you take n common from this, it will be n cube. So it will be 2 plus 4 by n, right? 2 plus 4 by n. And if you take n common from this, and from this, it will be n cube. N cube and n cube will cancel out. So in the denominator, you got 2 minus 1 by n, 2 plus 1 by n, 2 plus 3 by n. If you put n tends to infinity, this term 0, this term 0, this term 0, and this term will be 0. So your answer is 1 by 4. Okay, 2 by 8, that is 1 by 4. It's a finite number. It's a finite number, right? So by comparison test, un is convergent or divergent. So we can say that by comparison test, summation un is convergent or divergent if Vn is convergent or divergent. Okay, but see our Vn, that is summation of 1 by n square, is convergent. Why? Because see, it's a p series, n to the power 1, n to the power 2, right? It's a p series where p, here n to the power p is 2, right? So it's a p series where p is 2, which is greater than 1. And you know, if p is greater than 1, then that p series will be convergent. So that's why Vn is convergent. So we can say that Vn is convergent, that means un is also convergent. So we can say summation of un is convergent. And what is the summation un? This is our given series. So given series is convergent. That's how we have to check. Okay. So in maximum number of cases, apply this. Find the limit, and if they don't give Vn, then assume Vn as I have told you, and find out limit n tends to infinity un by Vn, and check if Vn is convergent or divergent. According to that, your series will be convergent or divergent, right? Remember this. These terms are extremely important. And maximum number of questions, if you take any number of questions, you have to first find out the n terms and then find out limit n tends to infinity un by Vn, and check if it's a finite number. If it's a finite number, then check Vn is convergent or divergent. According to that, your un will be convergent or divergent. So let's see another question, and then we'll move forward to our next topics. Test the convergence of the series summation un, where un is n cube plus 1 to the power 1/3 minus n. So let's see the solution. U of n is n cube plus 1 to the power 1/3 minus n. See, we can write this as, if we take n cube common, it will be 1 plus 1 by n cube to the power 1/3 minus n. Now, if you expand binomially, if you expand this is n cube to the power 1/3 So you will have n outside, and if you do binomial expansion here, you get 1 plus nx. N is 1/3, x is 1 by n cube, plus n into n minus 1 by 2 factorial into x square, that is 1 by n cube square up to infinity minus n. So this n into 1 and this minus n will cancel out, and if you take n square common from these terms, first of all you have to multiply it by n. So here you will have n square terms. Here you will have n to the power 6 and 1 l will cancel out. You will have n to the power 5. If you take n common from denominator, it will be n square common from denominator. It will be 1/3 minus 1 by 9 if you calculate 1 by n cube in this way up to infinity. Okay. Now let us consider that our Vn is this term 1 by n square. This is your V of n. Okay. Now let us consider that summation of Vn is 1 by n square. This is your summation of Vn term. So we know that we have to check limit n tends to infinity u of n by v of n. So this is limit n tends to infinity. If you divide by this u of n, this is your u of n, by v of n by 1 by n square, this n square will cancel out. So you will get 1/3 minus 1 by 9 into 1 by n cube up to infinity. If you put n tends to infinity, all the terms will be 0, you will get 1/3. So it's a finite number, right? It's a finite number. So hence by comparison test, u of n and v of n will be converging or diverging according to Vn is converging or diverging. But our here v of n is summation of 1 by n square, right? And it's a p series with p equals to 2, that is greater than 1. So that means it is converging. So you can say that summation un is also converges. Summation un converging is also converging. Okay. Now let us see our next test, that is D'Alembert's ratio test. D'Alembert's ratio test. So let summation n equals to 1 to infinity u of n be a series of positive numbers such that limit n tends to infinity u of n plus 1 by u of n exists finitely and let limit n tends to infinity u of n plus 1 by u of n is L. The series summation n equals to 1 to infinity u of n is convergent if L is less than 1 and divergent if L is greater than 1 and when L equals to 1 test fails. Okay, now let us see one question: how to apply D'Alembert's ratio test and where to apply and which type of problem we can apply D'Alembert's ratio test. So let's see one question. Test the series. One plus x by 2 plus x square by 5 plus x cube by 10, this series. See, we have seen in the theorem that character of convergency remains unaltered by the addition or removal of a finite number of terms. So from this we can omit the first term, right? So let un denote the nth term of the given series. So here nth term would be x to the power n by n square plus 1. See, if you put 1, it will get x by 2. If you put 2, you will get x square by 5. So this is your un. So what would be, to apply D'Alembert's test, we need u of n plus 1. And then we will apply limit n tends to infinity u of n plus 1 by un. According to that, we will judge. So what is u of n plus 1? This will be x to the power n plus 1 by n plus 1 square plus 1. So this would be x to the power n plus 1 by n square plus 2n plus 2. So let's find out limit n tends to infinity u of n plus 1 by u of n. So limit n tends to infinity, this is this thing by this thing. So it will be x to the power n plus 1 to the power x to the power minus n. So it will be x to the power 1 and it will be n square plus 1 by n square plus 2n plus 2 multiplied by x. Okay. Now take n square common from this and take n square common from this. You will get limit n tends to infinity 1 plus 1 by n square divided by 1 plus 2 by n plus 2 by n square multiplied with x. If you put n tends to infinity, this will become 0, this will be 0, this will be 0. Okay. So 1 multiplied by x, you will get x. Now, according to D'Alembert test, this value, that is L value, is x here. If x is greater than 1, it will be divergent. If x is less than 1, it will be convergent. And If x is equals to 1, the test fails. So let us say when x equals to 1, u of n will be 1 by n square plus 1. And we know that 1 by n square plus 1 is less than 1 by n square. So this is our Vn. Vn we can take as 1 by n square. Okay. So definitely u of n, this is u of n, this is v of n. So u of n is less than v of n. But we know that v of n 1 by n square is convergent because it's a p series where p is 2, that is greater than 1. So v of n is convergent. Okay. So by comparison test, we can say that summation un is convergent when x is 1, right? So ultimately we can say the given series is convergent when x is less than or equals to 1. Now let's see another question to clarify this. D'Alembert test. Trace the series. This is the question. The series is 1 plus 2 square by 3 square into x plus 2 square into 4 square by 3 square into 5 square into x square plus 2 square, 4 square, 6 square by 3 square, 5 square, 7 square, x cube, and x is not equals to 1. So here also you will apply the same method, that adding or removing some terms do not affect the convergency or divergency. So we'll omit this first term. So our nth term would be 2 square, 4 square, 6 square up to 2n square divided by 3 square, 5 square, 7 square up to 2n plus 1 square into x to the power n. See, if you put 1, then you have to take one term, that is 2 square. If you put 1, then it will be 2 plus 1, that is 3 square, and this is x. If you put 2, then you have to take two terms, that is 2 square, 4 square by 3 square by x square into x square, right? That's how this series will go. Now what will be u of n plus 1? It will be 2 square, 4 square, 6 square up to this 2n will be there, and we are adding one extra term, that is 2n plus n plus 1. In place of n, we have to write n plus 1. So it would be 2n plus 2 square upon 3 square, 5 square, 7 square. 2n plus 1 square would be there. It would be 2n plus 3 square. In place of n, we have to write n plus 1. So 2n plus 2 plus 1, that is 2n plus 3 square. And this would be x to the power n plus 1. So let us find out u of n plus 1 by u of n. So if you divide this thing by this thing, you will get 2n plus 2 square by 2n plus 3 square, because all the terms will cancel out, into x to the power n plus 1 by x to the power n. So it will be x to the power n plus 1 minus n, that will be x. Now if we take n common from this, it will cancel out, and it will be 2 plus 2 by n square, 2 plus 3 by n square into x. Because see, we have to arrange in this manner, because we know that we have to limit n tends to infinity. So limit n tends to infinity, u of n plus 1 by u of n would be limit n tends to infinity 2 plus 2 by n square by 2 plus 3 by n square into x. This will be 0, this will be 0, 2 square is 4, 4 by 4 is 1, that is x. So again we can say that this will be convergent if x is less than 1, and it will be divergent if x is greater than 1, right? And this depends on x value. So I think you got the point how to apply real numbers ratio test. Okay, now let us move forward to our third test, which is Cauchy root test. Cauchy's root test. So here let summation n equals to 1 to infinity u of n be a series of positive numbers such that limit n tends to infinity u of n to the power 1 by n exists finitely, and let limit n tends to infinity u of n to the power 1 by n is L. Okay, now if this L is less than 1, then it will be convergent, and if L is greater than 1, it will be divergent. That's all you have to remember. And when to apply Cauchy-Root test? When there is the format is in this format, u of n to the power 1 by n. If there is any format looking like this, you have to apply Cauchy-Root test. So let's see one question. Examine the nature of the series. Series is 2 square by 1 square minus 2 by 1 to the power minus 1 plus 3 cube by 2 cube minus 3 by 2 to the power minus 2 plus 4 to the power 4 by 3 to the power 4 minus 4 by 3 to the power minus 3. So see, here power is there. So that means definitely we have to use Cauchy's root test. So our first target is to find out the nth term. So what would be the nth term? So we can write nth term as n plus 1 by n plus 1 minus n plus 1 by n. to the power minus n. If you put 1, you will get 2 square by 1 square, and if you put 1 here, so 1 plus 1 is 2, 2 by 1, and this is minus 1, minus n minus 1. If you put 2, you will get this term. If you put 3, you will get this term. So this is the challenge, and keep your observation very high to write down this nth term. Once you write down the nth term, the sums will be very easy. Now what we need? We need un to the power 1 by n in order to apply Cauchy-Root test. So if you multiply by 1 by n and 1 by n will cancel out. So you will get, we are dividing by n here. So 1 plus 1 by n, if you take common, it will be 1 plus 1 by n to the power n minus 1 to the power minus 1, because this n and 1 by n cancels out. And see here we got 1 plus 1 by n to the power n plus 1, and in this we can write 1 plus 1 by n to the power n into 1 plus 1 by n. So we have taken common this term 1 plus 1 by n outside. So we remain with 1 plus 1 by n to the power n minus 1. Okay. Now if we take this term out of the power, so it will be 1 plus 1 by n to the power minus 1. We remains with 1 plus 1 by n to the power n minus 1 to the power minus 1. Now apply limit here. So limit n tends to infinity, u of n to the power 1 by n will be limit n tends to infinity 1 plus 1 by n to the power minus 1 into 1 plus 1 by n minus 1 to the power minus 1. Now if you put n tends to infinity, it will be 0, it will be 0. So ultimately you got 1 plus 0 to the power minus 1, and this limit n tends to infinity 1 plus 1 by n to the power n is e. Okay. So you will get 1 plus 0 to the power minus 1 into e minus 1 to the power minus 1. Now see, it is 1 by e minus 1. Now we know that e lies between 2 to 3. So that means e minus 1 will lie between 1 to 2. We are subtracting 1 on both the sides. That is 1 by e minus 1 will be less than 1. Okay. So that means this value is less than 1. So we know that in Cauchy's test, if this value, L value, is less than 1, then the series is convergent. So we can say that it is convergent. I think you got the point how to calculate this. Here all the formulas are same. Let's move forward to our next test, that is number 4, that is RAPS test. RAPS test. Pardon me if I pronounce it wrong. Let summation n equals to 1 to infinity u of n be a series of positive numbers and suppose that limit n tends to infinity, n into u of n by u of n plus 1 minus 1 is L. Now, if this L is greater than 1, the series will be convergent. If L is less than 1, this will be divergent. If L is equals to 1, the test fails. Test fails. Now, let us see in which type of problem we can apply RAPS test. Okay. So let us see one question from this. So our first question is, test the convergence of the power series x by 1 plus half of x cube by 3 plus 1 into 3 by 2 into 4 into x to the power 5 by 5 plus 1 into 3 into 5 by 2 into 4 into 6 into x to the power 7 by 7 up to infinity x greater than 0. So here again we'll omit this first term and our nth term will be 1, 3, 5 up to 2n minus 1 into x to the power 2n plus 1 by 2, 4, 6 up to 2n into 2n plus 1. This is the challenge, where we can observe that first term is 1, second term is 1, 3, third term is 1, 3, 5, right? So it will go in this way. And if you observe x, this is x cube, x to the power 5, x to the power 7. So it must be x to the power 2n plus 1. Because if you put n equals to 1, so it will be 3. If you put n equals to 2, it will be 5. So it will be x to the power 2n plus 1. And in the denominator, you can observe that this is 2, 2, 4, 2, 4, 6. So it will be the nth term, 2, 4, 6, 2n. Even term. This is odd term, right? So this should be 2n minus 1. And how to write this? 3, 5, 7. This is odd term. So you can write it as 2n plus 1. If you put 1, you will get 3. If you put 2, you will get 5. So this is our nth term. Now let us write u of n plus 1. So this would be 1, 3, 5 up to 2n minus 1. And in place of n, we have to put n plus 1. So it will be 2n plus 2. 2n plus 2 minus 1 is 2n plus 1. Divided by 2, 4, 6 up to 2n. And here you will get 2 into n plus 1. So 2n plus 2. So ultimately we got 2n plus 2. And here we will get, this is x to the power 2i's n plus 1 plus 1, that is x to the power 2n plus 3. And this term will be 2n plus 3. Now let us find out u of n plus 1 by u of n. So if you divide this term by this term, all the other terms will cancel out, and this is x to the power 2n plus 3 by x to the power 2n plus 1, so it will come outside, come on the numerator. It will be 2n plus 3 minus 2n minus 1. So ultimately you get 2n plus 1 square by 2n plus 2 into 2n plus 3 into x square. So take n from here, you will get n square outside. Take n from here, take n from here. So n square will cancel out. So you get 2 plus 1 by n square upon 2 plus 2 by n into 2 plus 3 by n into x square. Now apply limit here. Limit n tends to infinity, u of n plus 1 by u of n. Okay. So limit n tends to infinity. This will be 2 plus 1 by n square by 2 plus 2 by n into 2 plus 3 by n into x square. If you put n tends to infinity, it will be 0, it will be 0, it will be 0. So the value would be x square, because 2 square is 4, 2 into 2 is 4. 4 by 4 and 4 will cancel out, you will get x square. So we can say that by ratio test, the series summation n equals to 1 to infinity u of n is convergent if x square is less than 1 and divergent if x square is greater than 1, right? But test fails if x square is 1. Now let us say for x square equals to 1. If we say x square is 1, so from this we get u of n plus 1 by u of n is 2n plus 1 square upon 2n plus 2 into 2n plus 3. So this will be 4n square plus 4n plus 1 divided by 4n square plus 10n plus 6. So what is our Cauchy root test? It is limit n tends to infinity n into un by un plus 1 minus 1, right? So let us try this. N into u of n by u of n plus 1 minus 1. This should be n into 4n square plus 10n plus, this is un by un plus 1, and we got un plus 1 by un, so it will be inverse. 4n square plus 10n plus 6 by 4n square plus 4n plus 1 minus 1. So after calculation you will get 6n square plus 5n upon 4n square plus 4n plus 1, right? Now apply limit here. Limit n tends to infinity n into u of n by u of n plus 1 minus 1. So if you will apply limit here, limit n tends to infinity 6n square plus 5n by 4n square plus 4n plus 1. So take n square common, from numerator and denominator, it will cancel out. So it will be limit n tends to infinity 6 plus 5 by n by 4 plus 4 by n plus 1 by n square. If you put n tends to infinity, this will be 0, this will be 0, this will be 0. So this value is 6 by 4, that is 3 by 2, which is greater than 1. And we know from Raph's test that if L is greater than 1, it is convergent. So we can say by Raph's test, the series summation n equals to 1 to infinity u of n is convergent, right? So hence the given series is convergent when x square is less than equals to 1 and divergent when x square is greater than 1. Okay, so I think you have understood how to apply Raph's test. So sometimes mixture of the problems are there, so you have to be very careful when to apply which ratio test. Now our next is alternating series. Alternating series. Series in which the terms are alternately positive and negative is called alternating series. If we take example, summation n equals to 1 to infinity minus 1 to the power n minus 1 into 1 by n. So that is, the series is, we put n equals to 1, 2, 3, you will get 1 minus half plus 1/3 minus 1/4 in this way. So this is a alternating series. Okay, and we have one theorem regarding alternating series. This is Leibniz theorem. Leibniz theorem. So let's see what is this. The alternating series. The alternating series summation n equals to 1 to infinity minus 1 to the power n minus 1 into u of n converges if number 1, the sequence u of n is monotonic decreasing, and number 2, limit n tends to infinity u of n is 0. Okay, so let's see one question regarding this. So our question is, test the convergence of the series 1 minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square, this. So by observation we can see that this is an alternating series. That means we have to apply Leibniz theorem. Okay, so this series can be written as summation n equals to 1 to infinity minus 1 to the power n minus 1 into u of n, where we can say u of n is 1 by n square. Okay, now let us find out u of n minus u of n plus 1. So this would be 1 by n square minus 1 by n plus 1 square. We put n plus 1 in place of n, it will be n plus 1. So if you take LCM, it will be 2n plus 1 by n square into n plus 1 square. This is greater than 0, right? So you can say u of n is greater than u of n plus 1. Okay, so that means it is monotonic decreasing, right? So we can say the sequence u of n is monotonic decreasing. And what is the second condition? Limit n tends to infinity, u of n should be 0. So let's find out. Limit n tends to infinity, u of n, that is limit n tends to infinity 1 by n square. So 1 by infinity is 0. So we can say that by Leibniz rule, by Leibniz theorem, the given series is convergent. The given series is convergent. Okay, I think you have got the point. Now our next topic is absolute and conditional convergence. An infinite series summation n equals to 1 to infinity u of n of real numbers is said to be absolutely convergent if the series summation n equals to 1 to n to infinity mod of un is convergent. Okay, this is the main condition. Now next point is an infinite series summation n equals to 1 to infinity u of n of real numbers is said to be conditionally convergent, is said to be conditionally convergent if the series summation n equals to 1 to infinity u of n is convergent but not absolutely convergent. Okay, so we have a theorem regarding this. Let's see this. If the series summation n equals to 1 to infinity u of n of real numbers is absolutely convergent, then it is convergent. Okay, we don't require to prove this. So let us see one question. Show that the series 1 minus half plus 1 by 3 minus 1 by 4 converges conditionally. Let's see the answer. So we can see that it's the alternating series, and this can be written as n equals to 1 to infinity minus 1 to the power n minus 1 u of n, where u of n is 1 by n. And we know that this 1 by n is a monotonic decreasing because 1 by 1, 1 by 2, 1 by 3. So it will decrease. So we can say that sequence 1 by n is monotonic decreasing. Okay, it's monotonic decreasing. Also you can say as un tends to 0, as n tends to infinity. If n tends to infinity, un tends to 0. Hence, by Leibniz theorem, the given series is convergent. Okay, but the series summation n equals to 1 to infinity mod of u of n, if you take this, that is all of the terms will be positive. This series is divergent. It's a p series, right? 2 to the power 1 to 3 to the power 1, 4 to the power 1, that is p is 1 here. And we know if p is 1, then it will be divergent. So we can say that the given series is conditionally convergent. The given series converges conditionally. Okay. Now let's see one more question and we will wrap up our lecture. Prove that the series x minus x square by 2 plus x cube by 3, this series minus 1 to the power n plus 1 into x to the power n by n is absolutely convergent when mod of x is less than 1 and conditionally convergent when x is equals to 1. So let's see the solution. So this series can be written as u of n is minus 1 to the power n plus 1 into x to the power n by n. If you put 1 here, you will get plus x. If you put 2 here, you will get minus x square by 2 because it will be 3. Okay. So if you take mod, so mod of un will be mod of x to the power n by n, and mod of un plus 1 would be mod of x to the power n plus 1 by n plus 1. If you take limit n tends to infinity, mod of un plus 1 by un, you will have limit n tends to infinity, this un plus 1 by un. It will be n by n plus 1 mod of x, because x to the power n plus 1 by x to the power n. So x to the power n will cancel out, you will have x to the power 1. So limit n tends to infinity, if you divide by n here, you will get 1 by 1 plus 1 by n. This is mod of x. If you put n tends to infinity, it will be 0. So it will be mod of x. So by D'Alembert's ratio test, by D'Alembert's ratio test, the series summation n equals to 1 to infinity mod of un is convergent if mod of x is less than 1 and divergent if mod of x is greater than 1, but test fails if mod of x is equals to 1. Okay, so we can say that the given series is absolutely convergent when mod of x is less than 1. Okay, so that's all. So I think you have understood that how to solve this type of problem. Okay, and this chapter is extremely important for your BTech, and those are doing BSc and other competitive exams, preparing for any competitive exam. So practice at least 20 to 30 questions from this chapter, because the only difficulty you will face how to identify that which test you are going to apply, and you have to find the nth term. Okay, these are the difficulties you will face. Otherwise this chapter is very interesting and it's a wonderful chapter, and definitely 15 to 20 marks question will come from this chapter. So that's all for today. If you like my videos, please like, share and subscribe, and comment in which chapter you need a video. I'll definitely upload that within 1 week. That's my promise. So that's all for today. Have a good day.